This is the first in a series of video-based lessons that will demonstrate the application of a special subset of linear programming models where some or all of the decision variables can have integer values. In addition to the applications presented in these videos, there will be several in-class integer optimization application exercises to provide additional practice and hands-on experience with practical integer optimization modeling on a variety of different problems. This material is covered in Chapter 15 of our textbook. We begin by discussing the motivation behind the development of integer programming models. For a number of linear programming examples we had thus far, even though the decision variables would ultimately be whole numbers or integers, it was reasonable to just treat them as continuous with fractions and then round up or down their optimal values. Production amounts, shipment plans, financial investments, etc. can all be handled by assuming the decision variables are continuous, although we understood that producing or shipping half of a unit of a particular product is not actually going to happen. On the other hand, there are many applications where assuming continuous values and rounding at the end just does not make sense. Deciding on how many workers to schedule for a particular shift, how many to hire or fire, whether or not to do a particular project, which one among a set of locations to choose for a distribution center, which job to schedule on which machine, etc., etc. These are all examples of problems where using continuous variables will simply not work. We cannot select 0.6 of a project to do and not do the remaining 0.4. We either do it, 1, or do not do it, 0. Rounding 0.6 to 1 is not the way to go. Similarly, we cannot schedule 0.3 of a job on machine 1 and 0.7 on machine 2. We either schedule the job on machine 1 or machine 2. Rounding does not work here either. There are examples where it is desirable to mix continuous and integer variables. We will show this on an aggregate planning model example with continuous production variables and integer variables related to the workforce hiring and firing. These are called mixed integer linear programming models, or MILPs. The pure IP problems involve only integer variables, with a special case of binary or 0-1 variables used to model selection, assignment, and other yes or no types of situations. This and the following slide describe a set of relatively standard integer programming models we often encounter in business applications. Workforce scheduling, or scheduling problems in general, are used everywhere from airline crew scheduling to manufacturing and retail. These problems deal with decisions or deciding on how to optimally schedule workers to meet customer demand with the objective of minimizing the costs associated with particular staffing schedules. Project selection models use binary 0-1 variables to decide whether or not to select a particular project based on the forecasted benefits while staying within the budget and personnel constraints. Set covering is a generic representation of a situation where we need to select a subset of locations that serve themselves and all the other locations in some optimal way, where the limits include the number of such service locations and of course the overall costs that need to be minimized. Assignment models deal with optimally assigning customers to service centers, jobs to machines, and other types of matching problems, with requirements that each customer is served by exactly one service center or each job scheduled at exactly one machine, all the while minimizing the cost associated with a particular assignment in dollar terms or in terms of time or distance, or some combination of these. Finally, or rather facility location models discussed in this chapter are similar to set covering, except that the facilities serving customers do not come from the existing list, but are added as new locations. The decision to include or not include a particular new location is evaluated so that the best decision can be made by serving the customers and doing so at the smallest possible cost. The last example we cover involves the situations where decisions need to be made whether or not to incur the fixed costs associated with a particular time period or product line. It may be better not to produce during a particular month or a particular product line because of the benefits of not incurring the associated fixed costs. For an interesting IP application in paper and steel industries, see example 15.2 on pages 517, 518 in the textbook. That is the cutting stock production at the bottom of the slide. So this is sort of the intro to this overall topic of integer programming, and it's a good place to stop.